I work mostly on metals, metal alloys, metal composites. I do both simulations and experiments. I'm interested in how metals behave when they're pushed to their limits. So, if you were to put something into, a situation where it's exposed to corrosion or radiation, or if it's, experiencing very high stresses or strains, or is deforming very rapidly. So people, talk about those things as extreme environments. So I'm interested in metals in extreme environments, you could say. But, I'd say that probably represents 80-90% of my work, and then I have another 10-20%, which is just opportunistic. I do interesting things as they come up. I guess from the technical perspective, we want metals that can survive extreme environments. So, if we can make a metal that behaves better under radiation, or that behaves better, when it's loaded at high strain rates or something like that, that's good for technological applications, like in nuclear energy or, in infrastructure and things like that. And I guess there are also sort of fundamental scientific questions that we try to answer. So, if you were to look at a metal from the microscopic level, how do the different parts of it contribute to the behavior? Right. So those are all open questions that we're trying to answer, sort of on a more basic science level. I guess by throwing curveballs, I don't know. I guess I like this. There was a. I wish I knew the actual reference, but there was a study that was done a while ago about retention in learning. Right. How do students retain information? What are the learning methods that lead to the best retention? One thing that I always ask students is, what's the method that leads to the least retention? And it's not surprising that it's lecture. So lecturing, there's very little retention in a lecture. There's more retention when you do sort of hands-on things, and the most retention is when you teach somebody else. So lecturing, giving classes is mostly a benefit to me, I think, because it helps me to understand the material better. I try to make it fun by just asking students lots of questions, encouraging them to ask me questions. I feel like a lot of students are way too shy. Like they feel like they can't ask a question. Like if they don't understand something, then they can't ask a question, which is exactly the opposite of what they should do. And I try to sort of coax it out of them. And I guess over time they become more relaxed and just willing to ask questions. But it's always hard, I feel, to get students to just feel comfortable enough to stop you and say, hey, wait a minute, that didn't make sense. I don't get it. A lot of times the reason it doesn't make sense is because I said it the wrong way, or I said it in a way that doesn't make sense or something. I can say it a different way, and maybe it'll be better the next time. Yeah. In the classroom, I guess it's just, I guess it depends a little bit. So I've been involved in teaching two very different kinds of classes. I've taught, graduate level classes for our Ph.D. students here in the department. And for them, what I really try to do is make it so that they are not just, sort of proficient in techniques, problem-solving techniques, but they really understand the fundamentals of a field, and so that they can solve entirely new problems, ones they hadn't seen before, just by understanding the fundamentals. Right? And that basically means that you have to know the fundamentals, and you have to also know the math to be able to deploy them in new and unexpected and previously unseen circumstances. That's very challenging, I find, because as an undergrad, you're mostly taught to solve problems using already developed techniques. You're learning solution techniques a lot of times in the undergrad setting, and so I think that transition is sometimes tough. The other class that I teach is a freshman engineering class. It used to be Engineering 111, now it's 102. And that's another sort of transition class, right? First year grad students are transitioning from undergrad to grad school. Freshmen are transitioning from high school to college. So, there's a lot of, I guess, setting of expectations, communication of standards and expectations. Things that could fly in high school don't fly anymore, right? So you have to sort of guide students through that transition. And so I think that a lot of, even though the focus of the class, especially Engineering 102 as it currently stands, is on programming, I think that a lot of, my job as an instructor in that situation is to communicate expectations like, yes, you have to turn in your work on time. No, there's not going to be a makeup. It's up to you to decide whether you want to turn something in or not. I'm not going to make you do it, but then you have to take responsibility, right? So it's basically just shepherding students through that transition, while at the same time offering them the support they need to, to really be successful in that transition. It's a fun field. It's, I think, a good fit for me because I'm interested in engineering and I'm interested in science, and material science and engineering has both engineering and science, right? So I can do things that are fundamental and use them for some application. I like that. It's also interesting. This is something that somebody pointed out to me recently. A lot of fields, like engineering fields or science fields, are created by sort of increasing specialization, right? So microbiology is like a form of biology that's micro, or molecular chemistry, or chemical engineering was split off from chemistry, right? So fields, as they become more specialized, tend to split. Material science is interesting in that it came about from the fusion, from the actual joining of many different fields, like metallurgy, ceramic engineering, plastics, biomaterials. All these things sort of developed in different areas, but then over time realized that there's sort of a common ground between all of those different things, and the field kind of agglomerated from different disciplines rather than splitting up, right? So it's interesting because now you're getting like all kinds of connections which didn't exist before. I like that. My family's in Texas, and I spent a lot of time growing up in Texas. So I think for me, it's just a big part of it is just being in Texas. But then another big part of it is just how fast Texas A&M is growing, how fast it's expanding. Coming back to material science. Something like 5 or 6 years ago, there were no material science departments in all of Texas. There still aren't any in any of the neighboring states, right? So, big gap. Now we have 3 material science departments in Texas. The one at A&M, there's one at Rice, and one at UNT. The one here is obviously the biggest, just because of the scale of the school. And so, the field is expanding rapidly, and Texas A&M is a good place for that rapid expansion to occur, just because, there's huge growth in the engineering school and, enormous expansion of the facilities and capabilities. And I think there's a lot of support for people who want to go off and do something new. You hardly ever, if you come up with an idea, you hardly ever hear no. Sometimes people might say, oh, try this, try that, but they're not going to say no, right? Whereas, in other places you might hit a wall, and here you don't really hit walls.